All right, hello. I want to redo a little bit of what we did in class because I think this is going to illuminate what we were talking about a little bit better for everyone. I think, I don't know, it seemed like only a couple of people were following what we were doing, so I want to do it again, and this hopefully will be more helpful. So, in class, we looked at a system of particles. I've got this system over here. And if you notice, one of those particles is a blue particle. We're going to focus on that blue particle in a minute. And we started out making that whole group of particles a solid so that they couldn't really move with relationship to each other. And they all were interconnected, right? Like with springs. But we want to think of them as a gas now. Okay, so they're all moving around, bouncing around, hitting each other. And they all have their own momentum. So let's look at the blue particle and think of it as being a system unto itself. Okay, so we're just going to focus on that one blue particle. And maybe it's a molecule. Okay, so it has atoms that it's made up of. And if we add and subtract all the internal atom bonds and all those things, all of those forces inside that molecule, they all balance out and they make it. So where am I at here? I'm right here. All right. They all balance out, and that makes it a whole thing, right? It makes it easy for us to see that one system. Okay, so that blue particle is our system. All right, we have cut out the rest of the system, and we're just focusing on our blue particle as the system. Just like we made the eraser the system when we noticed that with respect to itself, the eraser had no velocity and therefore no kinetic energy. Well, we're doing a similar thing. We're just looking at the one particle. Okay? So, the external forces on it, okay, as long as it doesn't bump into any other particles, the external forces are going to be zero. Okay, so it's net, this F net, that F net equals zero. Okay, it's not hitting anything else, it's in between hits. Okay, and it has a certain momentum in between hits. That momentum we can see right here is right here. Okay, so that's our momentum for that guy, and F net is equal to zero. But also F net equals this equation here, okay, which is really dp dt. And if we're only summing over that one particle, then if this equals zero, if you take the derivative of something and it equals zero, that means that whatever that thing is a constant. So it has to be, our momentum has to be constant. So initially, let's say just after a collision, it's initially, we're looking at it here. Finally, before it has another collision, we look at it, it has the same momentum, okay? So our system maintains its momentum because it's not colliding with anything. And this is really easy to say, right? And just so that you guys can see it one more time, we have a P initial and a P final. And as long as no external forces act on it, that is going to be true. Okay, so now we're going to look at the entire system of particles in the box. And we still have no external forces, okay? There's no external forces acting on this box. However, we know that each one of those little particles in there are going to be bouncing around, hitting each other. And none of them have the same momentums, okay? They might have similar masses, but they're not going to have velocities that are the same. They're going in all different kinds of directions. So to illustrate that, I'm gonna grab one of these guys and I'm gonna put a velocity on it, right? And then we can come over here and put a velocity on that one. So they're all going in just crazy directions, and they don't care, and then they smack into each other all the time. All right. So adding up all these various momentums from all the j particles that there could be in there, all the way from j equals 1 to n, leaves us with an overall constant momentum. Okay? So that's our overall constant momentum. And if we looked at some time t, so our initial, t initial, and then we look some later time f, after collisions have happened, we have a delta t of t final minus t initial. Okay? So we look initially, we look finally, and when we do, we notice that after adding up all of the particles' momentums together, we add it all up, we find that the initial momentum and the final momentum were the same. Okay? So, let's recap. For momentum to be conserved, the system must have no external forces acting on it. So, we are trying to conserve momentum, and for us to do that, no external forces can act on our system. Okay? And now we have defined the system as the whole box. Okay? When an external force acts on the system, then the momentum is changed. Okay? So if we add an external force, then the momentum is changed. So hopefully that's a little bit more clear about what we were talking about in the conservation of momentum. So now we've got 2D momentum. So let's look at these things in 2D, because P is a vector, right? So we've got this vector, and now let's think of this as we're dealing with the blue particle again. It's hard to not put your hand down and write. It looks so bad. Let's try this again. Blue. It's like I'm a kindergartner. Okay, so we've got blue, and initially, before, at time 0, we are looking, and the particle has a certain momentum, and it has we can break that into components. We decide what our x and y coordinates are, and we break that down into the components for each of those x and y, and we see that before and after, as long as nothing is acting on this particle, nothing is acting on our blue body system, then we have a before and after that are the same. So now we're going to introduce into our system another particle. Okay, so M2 and M1 are going to collide. So M1 and M2 will collide elastically. Let's do it elastically. It doesn't matter, but we're going to do it elastically. So that we've got our initial momentum. That's going to be the initial momentum of each of the particles added together, okay? So we're going from 1 to 2, n equals 2 in this situation. So it's easy to write out n equals 2. We've got P10 here and P20 there. We know that's going to be a constant, all right? We've shown that already, hopefully. And we're going to do the same for final. And we're going to note that PJF is also a constant, the sum of those two things. So we're going to add this one to this one. These are not the same. The particles have changed their velocities. So individually, not the same. But adding them up together, and you know what? We need vectors on these guys. Adding them up is going to give us a constant. Okay, so that constant makes these two things equivalent. Okay, so P naught and PF are equivalent. Now, so we're doing it. We have to break up the P vectors into their X and Y components. So let's come on over here, and we're going to do some angle theta there. We've got our P2X, and that's initial. And we've got P1X initial and some theta. Oh, we need numbers on that. Theta 1 and theta 2. And then we're going to have our PY, which I want to write it in the same P1Y initial. And this guy is P2Y initial. Okay. We have to do the same thing with the afters. Okay, so here's our afters. This would be theta 2 final. This is theta 2 initial, theta 1 initial. Here we have, let's come out here so we can easily draw our theta 1 final. And it's going to go something like this. Okay? All right. So we have to break these things up into their components. So let's do it. Initially, let's do our initial. Initially, we have in the X direction, we're going to have P1X naught plus P2X naught. And we're going to have an initial Y. In fact, I'm not going to put vectors on top of this because we know which direction these things are going. All right. And I'm handling my negatives and positives from my diagrams. Okay, so I can tell which ones are negative and which ones are positive, how they lay in my coordinate system. So I can come over here and I can say P1Y initial plus P2Y initial. All right, so we know they're all going in the J hat or I hat direction, so I'm not going to put vectors on there. And then, like I just said, we have to look at which ones are positive and which ones are negative. And it looks like P1Y0 is positive and P2Y0 is negative. So let's make that negative. Okay, and now, good. And we can say what those actual things are. So we've got P1 initial times the cosine of theta 1 initial, and we're going to add to that P2 initial times the cosine of theta 2 initial. And we're going to do the same thing down here. We've got P1 initial, but this time we're multiplying by the sine of theta 1 initial. And over here we've got P2 initial times the sine of theta 2 initial. All right? Now, X and Y are totally different, right? One's happening in one direction, one's happening in the other. We need to keep those independent, okay? But we're still going to conserve energy between them. Or energy. We conserve energy all the time. Conservation of momentum is what we're talking about here. So we're going to conserve our momentum. And so what we say is, in each of the directions, P naught X totally equals P final X. And we're going to do the same for Y. So P naught Y is equal to P final Y. Okay. Now we can break those things down as well. P final X. I'm not going to write the, oh boy, maybe I should, because I missed my negative sign again. Maybe I should. Let's do it so that we have our negative signs at least done properly. P final X. What is that going to equal? That's going to equal our P1 X final plus our P2 X final. And we can break that down into P1 final times the cosine of theta 1 final. And we're going to add P2 final times our cosine of theta 2 final. And then our P final Y is going to be our P1 Y final. Now, is that one positive or negative? That one turns out to be negative. So let's stick a little negative sign on there. And we're going to add in P2Y final. And so I'm going to flip them around. I don't like having a positive in front. So, okay, well, for the sake of keeping things, all the P1 final, sine of theta 1 final. I'm just going to, for the sake of keeping ones and twos all in the same, I'm going to do it this way. P, what do we got? 2 final times the sine of theta 2 final. Okay, but we already know this, right? So we can start equating things. So we can take this guy and equate them. We can take this one and equate them. And that's going to give us two equations. Okay? So let's see where I'm at here in my notes. Fine. That's good. Fine. Those things are equal. Great. What about P initial in general? So P initial totally is equal to P final. We'll put some vectors on there. And if we were to say what P initial was, we would say that it's really P1x plus P2x in the I hat direction. And we're going to add P1y plus P2y in the j hat direction. And so essentially what we're doing is and I really should have a little knot in there, right? Essentially what we're doing is we're saying that P naught x in the I hat direction plus P naught y in the j hat direction. I wanted to check my notes above to make sure. Okay, so we're doing this, all right? How do we figure out the magnitude of that? We're going to figure out the magnitude by taking our P naught x, squaring it. We're going to add our P naught y and square it, and then take the square root. All right, that's one thing. What about the angle? Initial angle, overall initial angle is going to be the arctangent, and we're going to take our P naught y and divide it by P naught x, just like that. So just like always, this is how we do it. Same thing goes for P final. Okay, so we would do P final, even though the components are different, right? Our components are different. We should end up with, didn't I just write initial? And what I really want to write is final. There we go. And so our theta final is equal to our tangent P final in y divided by P initial in x. Oh my God. So many little things. P final in x. Okay. Okay. We're going to now talk about what exactly is conserved again. Because hopefully you guys understand that this and this are conserved, but the individual ones, the things that make up those little individual things, those are all changing, but they change in a way where if you still add them all up together, they are conserved. Okay, so it's the P naught that is conserved with the P final, and it's the overall. All right, so this is conserved. This and this not conserved. This and this not conserved. Okay, So it's the overall. You got to add them all up in each direction before you can say you've got conservation of momentum. We can get a little bit even better than this. Our initial theta and our final theta, if the directions are conserved, then what does that mean? Our initial theta and our final theta have to be equal. So these should be equal. All right? Those should be conserved as well. For those to be conserved, that means that P naught y divided by P naught x equals P final y over P final x. Now, they could be different numbers. This could be a different number than this as long as the ratio stays the same. So that doesn't tell us 100% that those are all equal. The ratio could still be the same. But right here, for this to happen, they have to be the same. So our P naught x has to equal our P final x, and our P naught y has to equal our P final y. So conserved all in the x direction and all in the y direction. Has to be. So that's our proof, okay? And that's how it breaks. That's how it shakes out. All right. Okay. So we're doing great. Everything's going great. Now we can go back and look at not just two particles. Let's look at all the particles in our box. So I'm going to draw a box over here. We're going to have all of our particles. Okay, lots of particles. And we just said what is conserved. We've got these two things that are conserved. So I'm going to write it all out. P naught x is equal to P naught, or P1 naught x plus P2 naught x plus P3 naught x plus ... all the way to Pn naught x. So that is the sum from j equals 1 to n of all the pj naught x's. Okay, that's going to equal our p final x, and we're going to write that out. So we have p1 final in x plus p2 final in x plus, and you guys get the picture, pn final in x, and we can then equate that. We can just easily rewrite that as the sum of pj final in x. Okay, and like we said, these two things are equal. However, this and this not equal. This and this not equal, right? They're constituents not equal. All right, it's the sum that's equal. Okay, let's do an example. We're going to do an example. So I think it may have been one of the students yesterday brought up billiard balls. Okay. Billiard balls, is a great example. So we're gonna do billiard balls. Billiard ball example. Now, our whole deal, here's our whole deal. We've got a before. Before, we've got this situation where there's an 8 ball, and we've got a cue ball, and the cue ball is coming in with some velocity. It's purely x. We're going to call that V1 initial. Let's call it V1 initial. And in fact, we could say V1 initial in x, all right, because it's purely in x, right? We don't have any x or y going on. And we've got that side pocket. The side pocket is exactly, well, not exactly. This angle is 53.0 degrees, but it's plus or minus 1.5. That means that it could hit here or it could hit here and still go in the hole, right? So this is our plus or minus 1.5 degrees. So as long as we can show that this 8 ball is within this range, finally, in our after, then it will go in. So after the collision, we've got our 8 ball. Let's call this number 1. And instead of the 8 ball, I don't like using 8s. So let's call that a number 2. Okay, so that's our number 2. And we're going to, this number 2, I don't know what the angle is going to be, but it's going to be theta 2 final. And that ball is going to be going in some direction. We don't know. And hopefully we didn't botch it so bad that we had it going in the opposite direction, which I have seen before. Okay, and then our number 1 ball is also going off, and it's going off with some theta 1 final. Okay, so we've got a theta 2 final and a theta 1 final. And technically, what do we want to know? We want to know if this equals theta 2 final. Okay, so that's what we're driving at. We need to know some stuff. The masses, mass 1 equals mass 2. They're billiard balls, so that's going to be actually quite helpful. But listen, guys, I can tell you right now, the test has M1 not equal to M2. So you're going to want to study it, maybe do the same thing, but change the size of the balls. Okay, change the masses of the balls. Size not necessarily, but the ball's masses for sure. Okay, what else do we know? We know that our V10 in the x direction is equal to 2.0 meters per second. We know that V1 final, but not in the x or y direction, is equal to 1.6 meters per second. So we know those two things. And let's see, what else? What else do we need? That's it. So we've got a before and we've got an after. And we just need to make sure that that ball is either... So the whole thing is we want to show that the 8 ball will or won't go in the pocket. And for us to say that it will or won't, we have to do this. Okay? We have to show theta 2 final is within that 53 plus or minus 1.5 degrees. All right, that's our goal. So let's see if we can do that. I don't want to go too far. We need our diagrams. How come my zero disappeared here? There. All right. So, before the collision, let's talk about before. Because really, essentially, what are we doing? We're going to say that P naught x equals P final x, and P naught y equals P final y. We're going to use both those two things. So we're going to have one equation and another equation. And we already know that initially we can say that that equals 0, right? So our P final y must also equal 0. So that's helpful. Not so much on the P naught x side, but let's go. Let's continue. P naught x, that equals our mass of our ball times our V1 naught x. Okay? P naught y, I just said P naught y is equal to 0, so everybody's happy there. And of course, the 8 ball, or ball number 2, is not moving, so we don't have to worry about it initially. This is the only stuff that has momentum initially. Okay. After the collision, so this is before, after, and you can tell when we're doing before and after because we're putting a little f there. So P final x, we want to say that equals P1 final x plus P2 final x. And that's fine, but what is P1 final x and P2 final x? So let's come over here to our little work area. P1 final x, that is our mass times V1 final times the cosine of theta 1. All right. We can call it theta 2 final if we want theta 1 final and theta 2 final, but there's only those two. So all the thetas are going to be final. So I'm not going to worry about adding an f there. P2 final x, that's the same mass times V2 final times the cosine of theta 2. All right, so there's that. So we can write that down as an equation in our x direction. In fact, let's just call all of this x direction. We'll deal with y in a second. So let's do all of that. Get rid of u. And we can say then that initially we've got m, so this is our real equation. This is the one we're really going to want to work with. V1 naught x. And we know both of these things. Well, we don't know the masses, but we don't care because watch. We're going to equal mv1 final cosine theta 1 plus mv2 final cosine theta 2. Okay, all the m's cancel, and we're left with this bit equals those things. Okay, that's our equation number 1. And we did that by looking at just the x direction. Now we're going to look at just the y direction. We have p naught y equals 0. Our p final y then equals 0, which equals our p1 final y plus p2 final y. And now we have to write out what those are. p1 final y is equal to m v1 final sine of theta 1, p2 final y is equal to m times v2 final times the sine of theta 2. Now, which one's positive and which one's negative? We can see here that the y of number 1 is negative. So we're going to come over here and we're going to put a little negative there. All right. And that allows us to say then that p1 final y equals p2 final y, or mv1 final sine theta 1 equals mv2 final sine of theta 2. The m's cancel, and so we're left with v1 final sine theta 1 equals v2 final sine of theta 2. This is our second equation. Okay, that's equation number 2. We're happy to see that. I'm going to get rid of these guys just to make it look a little bit nicer. Lovely. Let's do that here too. I like it. Nice. So we've got one equation and we've got a second equation. What do? We're really, keep in mind what we're looking for. What are we looking for? We're looking for theta 2 final. Okay, right up there. You can see it in top right, theta 2 final. Okay, so theta 2, that's what we want. But if you notice, we've got the cosine of theta 2 there, and we've got the sine of theta 2 there, and they're both multiplied by the same thing. So we can then say, if we divide 2 over 1, we're going to have v2 final sine of theta 2 over v2 final cosine of theta 2. I think you guys know where we're going with this. That's going to cancel with that, and we're going to be left with the tangent of theta 2. Nice. What do we have on the other side of our equations? So we're dividing 2 by 1, so we've got v1 final sine of theta 1 over... Now, we had to solve number 1. So let's solve number 1 for v2 final cosine theta 2. That equals v1 naught x minus v1 final cosine theta 1. Okay, so that equals this. This is really our preferred number 2 equation. So I have to put in the bottom v10x minus v1 final cosine of theta 1. Now, if you notice, we know this. Oh, gosh, you know what? You're like, no, we don't know that. But yes, we do. And I apologize. Theta 1, this theta 1 right here is 37 degrees. Okay. All right, so let's go back down here. We do know theta 1. So we've got the cosine of theta 1 and the sine of theta 1. Those are known. We're given this, and we're given this. So all of that is known, and all we really want to know is theta 2. So we can say that theta 2 is equal to the arctangent of all that stuff, and we can start plugging in those numbers. V1 final is 1.6. We're going to multiply that by the sine of 37 degrees. V1 naught x, that's 2.0 meters per second. We're going to subtract off 1.6 times the cosine of 37 degrees. Okay? So this whole number equals 1.33 something, maybe even another 3, I don't know. But if we take the arctangent of that, we end up with 53.13 degrees. And that is within the range. So theta 2 is in 53 plus or minus 1.5 degrees range. And the ball goes into the hole. Yay, we won the game. Okay, so we still have some stuff to do. I still want to do center of mass, earth mass systems, and that. So we're going to do that in the next vid.